So here's where things stood after the discovery of the electron and the discovery of radioactivity. J.J. Thomson proposed a model for the atom that looked something like this. There are a certain number of electrons in the atom that you can knock out. For example, for a lithium atom, you can knock 3 electrons out of the atom. There must be, since the atom is neutral, there must be a positive charge in there that balances off every one of the little negatively charged electrons. And he pictured the positive charge as being kind of spread out like a goo. And he called this the plum pudding atom. You can see why. The electrons are like little plums. And the cake part of the pudding, see, a pudding in England is more like a fruitcake than what we call pudding in the United States. But the cake part is all positive. You can think of this as a blueberry muffin model if you want. The positive part is spread out and kind of soft. Now, how do you explain how cathode rays get generated? Well, when you agitate this, when you heat it, when you slam other plum pudding atoms into it hard, you can knock some of the plums out of the pudding. And what will happen is you'll leave a little hole behind, and then your electron, your plum, will fly out. So that's how he pictured how the cathode ray was being generated. So this could explain some things like that. You could also explain electrical conductivity like that, because if you had another plum pudding atom over here that had a hole in it, a missing plum, this one could go and replace it. You could get kind of a domino effect thing and explain electrical conductivity that way. But there was a lot that it couldn't explain, like how do atoms hook up to make molecules? All right, so one of Thomson's students, Ernest Rutherford, decided to do a test on the plum pudding model. And it involved the alpha particles that we were just talking about. He said, let's imagine we've got a couple different models of the atom here. Here we have hard atoms with some distance between them. So these are the atoms, little hard spheres, something like what Dalton and what Democritus pictured. They were indestructible, right? So there's nothing you can do to them. Now bomb them with some alpha particles. You'll see some of the alpha particles are going to get through, but any of them that hit the atoms are going to bounce back. And actually, depending on how close together these are, a lot of them are going to bounce back. So you're going to get alpha particles fired at hard spheres, many ricochets. Some pass through. But what if you have the plum pudding atoms? They're kind of squishy. They're spread out positive charge. They're not hard like these things. And the alpha particles, remember, were positively charged, we said? If they hit these things, they're going to be able to kind of plow through the soft, cakey part. They might swerve a little bit because the cakey part is positively charged. So if you have plum pudding atoms, you should see all pass through. So it should be one or the other, depending on which model you've got. had some idea about the size of the atom and the distance between them, so he could actually calculate how many should ricochet from a hard sphere and how many should go through with a plum pudding. And this experiment, where you're going to fire some alpha particles at a bunch of atoms, should tell us which one of these models we've got. The big surprise in this experiment was that neither of these models was correct. So let's back up and look at the experiment a little bit. We need a source of alpha particles to shoot at our atoms. So we'll take our radiation projector that we've already talked about. Put some radioactive stuff in the hole in a lead block. Here's the radioactive stuff. Rutherford used radium. It is very good at emitting alpha particles. Here are the alpha particles spraying out of the hole. And we got to have our atoms over here, and it should be a pretty thin film of atoms. Now, there's a lot of metal foils that you can pound very thin. One good one for this experiment would be gold. So you can take a gold and you can pound it with a hammer until you get a sheet that is so thin you can see through it. So it could be gold foil, could be some other metal, as long as it was thin enough foil. And you're going to put some kind of a detector here. And how about film is easy? Because when an alpha particle strikes film, it will expose the film, remember? And it'll leave a little spot. So here's what he was expecting. He would expect that the beam would pretty much go through the foil and punch right through if it was plum pudding. And it might, since the plum pudding atoms would swerve a couple of the alpha particles just a bit, it might fan out just a little. And from this, from how much the alpha particle impacts here fanned out, he was hoping to figure out something about how concentrated the positive charge was going to be. So that's what he expected. What he got was a different story. Here's what he actually got. The alpha particle beam hit the metal foil, and just like expected, most of the beam went through. But there were occasional wild deflections, and some even bounced back like that. So most of them went straight through. There were a few large-scale deflections, and some of them actually ricocheted. So you're getting a situation that was neither of these two situations we talked about before. There were almost all of them passed through, but there were a few ricochets. So it couldn't be hard spheres, or there would have been more ricochets, and it couldn't be plum pudding, or they all would have passed through with no ricochets. So what could have caused this kind of thing? He said this was as surprising as if you fired a rifle bullet at a piece of tissue paper and it bounced back at you. A mortar shell, actually, is what he said. So here's the picture. Suppose these are your atoms. And instead of plum pudding, all of your positive charge is crunched into a tiny, hard little kernel or pit in the center. And the rest of the atom is where the electrons hang out. And there's not, it's mostly empty space where the electrons hang out. Now try to explain the pattern that you see up here, the scattering pattern. Well, most of the alpha particles are going to go straight through, but occasionally one of them is going to be unlucky enough to hit a nucleus straight on, and it can bounce back. Every once in a while, one of them will glance off a nucleus and hit this way. And we're going to see the same kind of scattering pattern then. This will explain the scattering pattern that we're seeing up here. So what we can conclude from this experiment is the existence of this tiny little hard pit. From the number of deflections like this and the number of ricochets like that, Rutherford was able to calculate the size of the nucleus. That little pit is called the nucleus. And it's about 1/10,000th the size of the atom. So here's what a hydrogen atom would look like. There's a nucleus in the center. It contains all the positive charge in the atom is all crunched into the center. And apparently from his calculations, this nucleus is massive. Almost all the mass is contained in the nucleus. It's all crunched into the center. And this is a very lightweight atom. Or, I'm sorry, a very lightweight particle here. The electron is, get the number right, 1/1836th of the mass of this nucleus in the center. And almost all of the mass of the nucleus in the center is the mass of the atom. So you can say it's, that's the fraction. So this weighs practically nothing, and it's roaming around in the empty space here. How's it roaming around? We don't want to be too specific about that. Rutherford was very specific. He said, well, maybe these are in orbits like planets around a sun. That turned out later not to be correct. And in fact, our picture of the electron as a little particle that's negatively charged turned out to be not correct either, not quite correct. There's a little bit more to it than that, but that is going to be the subject of Chapter 3 of Module 3. We'll talk more about that then. So this is the Rutherford atom, and it explains Rutherford's experiment. Now, there is a video below this one that shows the actual setup for Rutherford's experiment, and I encourage you to watch that.